I'm waiting for this thing to start recording. Yes, I got the message. Okay, voltage regulators. Remember, we started the first part of the voltage regulator. We already did it, but we are going to revisit it just to recap on what is done. Okay. A voltage regulator. Okay, sorry. Let's try to recap on power supplies. A full-wave bridge rectifier with a capacitor filter generates a DC voltage, VDC. However, this VDC is susceptible to line regulation, load regulation, in addition to ripples. Those who already started with that full-wave bridge rectifier practical, you could identify that. A voltage regulator is an electronic circuit that provides a constant VDC even if the line voltage or the load current changes. Okay, so a voltage regulator has two functions. It basically compensates for line regulation, and it also compensates for the load regulation. We studied about line regulation and load regulation when we did Zener diodes. We even have a formula for that. Okay. So a voltage regulator is basically an electronic circuit that compensates for line regulation and load regulation. In addition, it can remove the ripples as well. Now, this is the last slide that we did under power supplies. So what do we have here? In a series voltage regulator, it's a block diagram representation. The direction of the arrow indicates direction of the signal flow. So we have VI unregulated. That is exactly so-called VDC we found under power supply. Full wave bridge rectifier with a capacitor filter. At the output, you will see V0 regulated. So the input to the system is VI unregulated. That is basically our VDC. The output to the system is V0 regulated. That is a constant VDC that is not supposed to be affected by line regulation, load regulation, and ripples. So between the input and output, there is something called control element. Now, look at the control element. There are two arrows coming in. One arrow here and another arrow coming there as well. So two arrows coming in, that means control element is receiving two inputs. The first input is called VI unregulated. The second input is called VE, that is an error voltage, ERROR, an error voltage. So control element is able to conduct based upon error voltage VE. When the error voltage is 0, control element cannot conduct. When the error voltage increases, control element is going to conduct. If error voltage increase further, control element is going to conduct more. Okay, that is control element. Now, we are going to look at this one, error amplifier. Look at the arrows. There is one arrow coming in and another arrow coming in here. So basically, this error amplifier also having two inputs. One of that input is called reference voltage. A reference voltage is a constant DC. That doesn't change at all. Okay, it's like a highly stable reference voltage. Now, we have a voltage called sampling voltage. Sampling voltage is coming from a sampling circuit. A sampling circuit is basically a voltage divider. We know when you connect two resistors in series to a battery, you get voltage division. So a sampling circuit is usually a voltage divider. Okay. What is this error amplifier is going to do? Error amplifier is going to look at VR and VS and find the difference between VR and VS, like VR minus VS. So basically you have a 5, if you have a 5 volt there, and if you have a 4 volt at this point, your error voltage will be like 1 volt. Got it? So error amplifier make a comparison between VR and a VS. Now, what is going to happen in this kind of a circuit? You can see there is something called a closed loop. Look here, from the control element through the sampling circuit, through the error amplifier, this is a closed circuit now. What's the problem with a closed circuit? If you got a rope and you tie two ends of the rope, and if you try to pull from 3 or 4 corners, you know what is going to happen. If you pull more onto your side, another person is going to move, right? Like that. This is a closed circuit. In a closed circuit, a stability is eventually reached. When that stability is reached, your V0 supposed to remain constant. Okay, let's go through the slide and we'll come back to the block diagram explanation once again. VR is a stable reference voltage that is independent of any changes in supply voltage. Sampling circuit generates a V sample that is directly proportional to V0. Remember the most simple explanation, a voltage divider. Error amplifier create an error voltage VE that is proportional to VR minus VS. Control element conduct according to the V error, thereby maintaining constant V0. That is the explanation of a circuit like this. Now, this is the time for questions before I move on with series voltage regulator. First, I want all of you to understand the concept very clear. Each block has a very dedicated job, a duty. And I want all of you to understand that first. Time for questions. Yes, Bota.
Yes, sir. I'm just wondering, what type of voltage will the error voltage be? Will it be an analog voltage or like a PWM signal or something?
No, it's standard. This is purely analog. So all the voltages are analogs.
Okay, because I knew some power supplies use like a PWM voltage to
There
regulate
is
as
those
well.
kind of power supplies are called switch mode power supplies, and
Okay.
that is too much above our level.
Okay. Okay, thank you.
This is purely analog voltage, and all the voltage you see here are mostly DC, because we are dealing with DC power supply.
Okay, thank you, sir.
Mosu,
So if this is DC, then why are the suffixed letters, like why are the letters there by the regulated and the unregulated small? Or is it just because this also applies to AC currents as well?
I think you are confused. For a DC, prefix and suffix needs to be uppercase.
Yes, sir, but isn't that I the small I? It's not a capital I.
There is only one has a capital small I. That must be a typing mistake. This is not taken from any textbook. I drew it physically myself.
Oh, okay. So I was a bit
This is
confused
the
because
only one that is a small letter. Thank you for reminding, but I cannot edit it here. This is
okay, sir.
already a PDF. I'll have to go back to my original diagram made in Visio.
Okay, sir. Thank you.
Any other question? Okay. Now, what I want all of you to remember is, in a series voltage regulator, there is a control element, basically conductivity of the control element, directly proportional to error voltage. Reference voltage is constant. Sampling voltage can change with respect to V0. V0 increases, your V sample increases. V0 decreases, your V sample decreases. So basically, this V sample is directly proportional to V0. But VR is always constant. So if VR is constant, VS is changing. Then the error voltage is difference between VR and VS. Okay, now in this case, what happens if V0 trying to increase? I'm putting an up arrow indicating V0 somehow try to increase. Your V sample is going to increase. What happened to VE? I want you to answer that question.
So it's going to decrease.
VE is going to decrease.
Yes, it's going to decrease.
Yes. V0 is increasing, V sample is increasing, VR is constant. Error voltage becomes smaller. Okay. Error voltage becomes smaller means control element is going to conduct less. That's what we already know, right? Error voltage is smaller, control element going to conduct less. If control element passing less current to the output, your V0 will decrease. Do you agree? Are you losing it out?
Sir,
Yes.
didn't we do this?
What?
Didn't we cover this part previously?
Series voltage regulator?
Yes.
I don't think so.
Or we are revising now.
No, there is no reversing.
I mean revise, recapping.
Revise, no.
Yes.
We did this block diagram, but we didn't go into detail.
Oh, okay, sir.
But I want you to understand this. Remember, it is not like V naught increase, V naught decrease. When V naught increase, V sample increase, error voltage decrease, control element conduct less, then V naught decrease. So it is going through one set of cycle, one complete cycle. And that's what I want you to understand. Are you all fine with it?
Yes, sir.
Okay, if that is fine, we can move into the next one. Okay, this is just a small recap. An NPN BJT need VBE 0.7 volt to make it conduct. Base needs to be more positive with respect to emitter. Okay. In an NPN transistor, base needs to have 0.7 volt more than the emitter to make it conduct. For a PNP also need absolute value of VBE 0.7 volt, but emitter needs to be more positive with respect to base. Okay, this is NPN and PNP BJTs. If you can understand this concept clear, then we can go through this chapter very quickly. Next point, a Zener diode in reverse bias keep a near constant voltage across it, that is VZ. And we also studied a detailed study about VZ equal to VZ naught plus IZ, RZ, things like that. And we also identified line regulation and load regulation with respect to a Zener. Okay, we need this 3 point, that is NPN BJT, VBE with base more positive. PNP also need a 0.7 with emitter more positive. Then Zener diode is going to keep near constant voltage across it, that is VZ. So we already know a Zener diode always connected in a reverse bias. Okay, here goes our first series voltage regulator. Let's try to identify what we have. At that point, that is VI unregulated, that is coming from a full wave bridge rectifier with a capacitor filter. And we already know what is this? What are the problem that we have with this? We have problem. There is line regulation, there is load regulation, and there are ripples. Now, between the input and the output, this is VL regulated. What do we have between input and output? We have a transistor BJT called Q1. Collector at the input, emitter at the output. Or basically, we have a voltage across collector and emitter. Look, there is a voltage VCE with collector more positive with respect to emitter. Okay, collector is more positive, emitter is negative. Or basically it says your load voltage can only be smaller than input voltage. Okay, we are losing some voltage there, but there is a benefit. What is the benefit? We are going to see soon. Okay, number one, we need to make an expression for VL. How do you make that? If you know this current, it is easy. IL times RL is VL. But IL, you will never know unless you remember what is this RL. RL could be your music player, maybe your CD player. So it is your mobile phone. It could be. When you charge, it takes some current from the charger, right? That is the load current. So RL is an electronic device usually. So how much exact current is flowing through that? Unless you measure, you will never know. So that is not going to help. What is going to help here is start from 0. Go up, go up, go up. You reached VL. Agreed? This one. Let me put an arrow. And look at this. These two are same. Do you agree?
Yes, sir.
They are equal because they are in parallel. Now, we can say that this VL is same as this voltage. Okay. So what can we write? Look the polarity of your Zener. Negative, positive there, and positive and negative on the other side. Or basically, this two, you can assume that these are two batteries. They are connected in series, but it is series opposing. So basically, you can say VL equals VZ minus VBE. Is it understandable?
Yes, sir.
So, looking at this formula, VZ is a constant. That is a Zener voltage. VBE, if the BJT is conducting, VBE is also a constant. That basically means VL also a constant. Can you agree to that?
Yeah.
Next point. I'm going to take it out. Okay. One, look at this resistance R. This resistance R is connected between collector and base of Q1, right? So there is a current that is flowing through that resistance. We call it IR. This IR is splitting into two different current. From this point, IR is split up into two current. One current makes up the base current, and the second current makes up Zener diode current, right? So IR split into two different current. One of that current is base current for Q1, and the second current is Zener diode current. Or in other words, you can write IR equals IZ plus IB. Do you agree to it?
Yes, sir.
Anybody else?
Yes, sir.
Okay. These things are quite simple because we are not using any complicated concepts here. Okay. The points. Zener act as a voltage reference. Look here, we have a voltage reference there, is it? Zener acting as the voltage reference. That is, we are comparing. Then, what is your Q1? Go back and look up there. What must be your Q1 according to block diagram?
The control elements.
Exactly. Why control element? Because we can see the position. One end of the control element is VI unregulated. Other end of the control element is V not regulated. Look here, you have the same. One end VI unregulated. See, one end of the control element is this VI unregulated. Other end of the control element is VL regulated. So from here we can say that your control element in this circuit diagram, it is Q1. We already identified Zener diode is the voltage reference. Okay, what else we have? We have a sampling circuit here. In here, you don't see a sampling circuit directly. There is no voltage divider that we are going to see. But there is something here. Go back, try to understand what is this VBE. Look here. VBE is VB minus VE. Do you agree?
Yes, sir.
Yes, sir.
So VBE is VB minus VE. In that case, trying to connect my camera here. Okay, this is VBE, very small. This is an NPN BJT. For an NPN BJT to conduct, base needs to be higher potential with respect to emitter. Agreed? Do you agree to that?
Yes, sir.
Your base needs to be, because that is N, this is P. P needs to be more positive. Let me write V B E equals voltage at the base minus voltage at the emitter. Do you agree to it?
Yes, sir.
Okay. Can you replace that VB with something? Look at the diagram. That is voltage at the base. Replace it with something that you already know. Hmm?
Can it be R multiplied by IB?
No.
Okay.
Isn't it RL?
Hmm?
VL.
Voltage at the base is VL.
So since you said that they are parallel, so the voltages are going to be the same.
VBE is this voltage. That is VL. You are forgetting about that. What is it?
So isn't it the voltage at the base?
That's VZ.
Because
This is VZ. VZ is up to that level. So VB is VZ. Are you getting it?
Yes, sir.
So I'm going to replace that VB with VZ minus. What is voltage at the emitter?
0.7.
Can you just stop this singing? Voltage at the emitter is 0.7. What concept are you using?
so it's the voltage at the load.
That is emitter. Emitter, you have the same voltage at the emitter, like VL. So I am going to replace VE with VL. So basically we have VBE equals VZ minus VL. So what you do is isolate that VL, move it to the left side. What do you get? VL equals VZ minus VBE. Are you getting it?
Yes, sir.
This is, we did find the same expression using another concept, because for a Zener diode, in reverse bias, cathode, that's point, is more positive. And for a VBE, base needs to be more positive with respect to emitter. So negative to positive, VZ, positive to negative, you say minus VBE. So VZ minus VBE is VL. We got it in two different ways now. In the first way, we are counting that root. Second way of doing, we rewrite VBE same as VB minus VE. We replace VB with VZ and VE with VL. And we just do just one interchange manipulation. VL is VZ minus VBE. This is a series voltage regulator. Any question before I turn off the camera? Okay. So we found quite a few things here. VL equals VZ minus VBE. That is confirmed. This current IR is splitting into base current and Zener diode current. So that is how we get this one. IR equals IZ plus IB. Now, we also understand Zener diode act as a voltage reference. VBE equals VZ minus VL. That is your feedback circuit. Okay, feedback circuit is same as sampling circuit. This one. Okay, you cannot directly see a voltage divider, but remember, this is the most simplified form of a Zener series voltage regulator. So basically, that sampling circuit is between base and emitter of Q1. Then Q1 is, of course, the control element. No one got a problem with that. Agreed. Okay. In this case, if you want to describe the operation of this circuit, what do? You simply assume VL increases like this. That arrow up indicating VL somehow trying to increase. If VL trying to increase, what is happening to VE? Sorry, VBE. Remember, voltage at the base is Zener diode, voltage at the emitter is load voltage. So this second one trying to increase. What happened to VBE? Silence.
So it will decrease.
Hmm?
It will decrease because
VBE will, because VL increasing means voltage at the emitter increasing, and voltage at the base is Zener diode voltage remaining constant. So VBE will decrease. VBE decrease means base current decreases. Base current decreases means emitter current decreases. Do you agree? Emitter current is beta plus 1 times base current. Because in this circuit, emitter current is the load current. If emitter current decreases, your output voltage will decrease as well. Now make a comparison between the first and the last. We started with VL increasing, we end up with VL decreasing. Anybody got a problem here? Again, silence.
No, sir, we don't have a problem.
We are moving to a problem. Let me find another sheet of paper. Study the circuit as I am preparing myself. I'm writing the data onto the same diagram. VI unregulated, 12 volt. You can see there, VZ is 6.2 volt. RL 11.7 ohms. Value of R is 470 ohms. And we have a beta of 50. Now the question is, calculate the voltage at every node and current through every component. Let's go back to the camera. This is the same diagram I am going to use. We have a 12 volt, that is your VI unregulated. VL regulated is the output. Beta for BJT is 50, R is 470 ohm. You have a Zener diode with a Zener voltage of 6.2 and RL is 11.7 ohms. Where do we start? See, negative, positive, positive, negative. That is, VZ minus VBE is VL. Remember, you don't even have to remember it as a formula. You can pick it up from the diagram. VL equals VZ minus VBE. That is 6.2 minus 0.7. What's the answer?
Five point five.
5.5.
What is next? VL we found. We know the value of RL, so we can find the value of load current. IL equals VL over RL. That is 5.5 over 11.7 ohms.
So I got 470 microampere.
170 microampere.
Sorry, I meant milliamperes.
Somebody confirm it.
Yes, sir. It's 470 milli.
117.
4
Like that. Sorry?
470.
It's 470.
470 milliamps.
That makes sense. Okay, we got IL. IL is this current, which is same as emitter current. Emitter current is 470 milliampere. Can you find this base current? Can you find the emitter current from the base current? Sorry, can you find the base current from the emitter current? IB equals and this is totally unacceptable. We just completed BJTs at DC. How do you find base current from the emitter current?
Emitter current divided by beta plus 1.
So I got 9.22 milliamperes.
Somebody confirm it.
Yes.
That's correct.
So we found base current. Next, we need to find current that is flowing through the resistance R. We call it IR. How do you find it? IR. How can you find that current? How do you find current through a resistance?
So it's going to be the voltage from I divided by the resistance of R.
What is the voltage?
The voltage, can we use the, I mean, it's the 12 volts from the I, since the voltage divider, it will be 12.
Is it
volts.
470 ohm connected from 12 volt to ground directly?
Oh, no, sir. So it'll be 12 volts minus the 6.2 volts.
So first, IR, basically voltage across R divided by R. That's our Ohm's law. Look, one end of the R is connected to 12. Other end of the R is same as your Zener diode voltage. So this is 12 minus 6.2 divided by 470.
So I got 12.3 microamps. Milliamps.
Make up your mind first.
So it's milliamps.
12.3. Somebody confirm it.
Yes, sir.
So we found IR. IR reaches at that point, it split into two different current, IB and IZ. That is IB. IB we already know. IR we already have. How do you find IZ?
It's going to be IR minus IB.
How much is IR?
IR is 12.34 milli
And IB is
9.22 milliamps.
and the answer is
The answer is 3.12 milliamps.
like that.
3.12, sir.
So we found Zener diode current. There is one more thing that you could find out. Power consumed in the Zener. Power consumed in the Zener is Zener voltage multiplied by Zener current. That is 6.2 multiplied by 3.12 milliampere. That is the power consumed in the Zener. How much?
.02 watts.
Give me in the proper unit.
19.34 milliwatts.
Somebody please confirm.
Yes, sir.
So power consumed in the Zener is 19.34 milliwatts. This is the amount of power consumed, wasted by the Zener diode. There is one more thing that you could find from here. What about the power consumed in Q1? Power consumed in Q1. P Q1 is basically VCE Q1 times IC Q1. How do you find the VCE? Look at the collector, what do you have? At the collector, you have 12 volt. What is the voltage at the emitter? 5.5. So VCE, basically, voltage at the collector minus voltage at the emitter, that is 12 minus 5.5. And what is the current through it? That is same as the load current. So VCE is 12 minus 5.5 multiplied by, and the current is 470 milliamps. This is the power consumed by the BJT, the control element. Anybody got an answer?
.06 watts.
That is the amount of power consumed by the BJT. Now you can see Zener diode is operating at much lower power levels. So BJT is the most power consumed element in this circuit. Of course, you can find the power consumed in every component as well. For example, you wanted to find power consumed by 470 ohm EC I squared R. You have IR. We got how much that current is, 12.3 milliampere. Square it, multiply with 470 ohm, you can find power consumed in that. You can even work out the power consumed in that resistance. Okay. In today's session, what we did is whatever we learned in BJTs at DC, the previous chapter, we applied into one of the power supply, a series voltage regulator circuit. So what we did so far is first step in designing a series voltage regulator. And using all the rules that we studied in BJTs at DC are applied in this problem. Okay. Now, in the next class, we go one more level deep. We try to define how well this circuit can operate. And after that, we will find the limitations of the circuit. Then we will try to improve on the circuit, and we will go one level higher. This is like going from one lower level into a higher level. The important point here is if you are not catching up the lower level, then at the higher level you will be lost again. So I recommend all of you to work out this problem, and all the answers are already here. See, everything is there already worked out. And you already have this video, so you can download and start learning it. In fact, you don't have to download. If you want to verify, answers are here. Okay, and I demand one more thing. That is, you have an LT spice with you. Take a BJT that you know, like 2N22 will do, and take a 6.2 Zener diode and put a 470 ohm resistance, put a battery 12 volt, and verify all these answers that you got. You need to verify, are you getting the same ones? You can take it as your this week's challenge, because this is the last class for the week for this group. All right, then bye for now, unless you have a question.